Expectation, as we've just defined it, measures on average the location of your random variable. It represents the average location of where it is located. The expected value of a random variable is also called the center of mass for that reason. Another important characteristic, I could tell you the average location, but you also might want to know the spread of that distribution, right? How spread out is this thing? Does it tend to be tightly clustered in the middle? Does it tend to be wildly distributed off the periphery, and so on and so forth? We'd call that the variance, and we could ask what would be the right way to measure such a thing. It's probably safe to say that a quantity that you'd want to look at is how far away you are from your average value. Okay, so it should measure how far on average a random sample of x is from its expected value. Because if you have very little variance, I should say, if you have very little variance, then you have some random variable that's like all concentrated somewhere, and therefore it would all be concentrated right near its expected value or its center of mass, so that would be very low. And so the most natural thing to look at here would be something like the absolute value of x minus the expected value of x. Okay, so I'll draw a picture to sort of roughly suggest what I'm trying to get at here. Let's say this is a PDF, and this is my, these are my axes rather, and here's my PDF. Okay, it looks like that, kind of a bell curve type thing. And let's say the expected value of x is right here. So expected value of x is this number here, whatever that might be. And so then you draw some samples, and you know one is here, one is here, one is here, and so on and so forth. And you'd say, well, I have a lot of spread, or my distribution is very spread out if these distances between the samples and the expected value are very high, right? If on the average a sample is very far from its expected value, you'd say, okay, this distribution is probably spread out quite a bit. So the most natural thing we would look at would just be the absolute value of x minus its expected value. So the absolute value of x minus expected value of x, just the average value of that. But we're engineers. We like being able to differentiate things, the doubly so for industrial engineers because we like optimization. And so instead of looking at the absolute value, we are going to square that distance. Okay, we're going to take x minus expected value of x squared. As a sanity check here, let's ask, is this thing here, I'll erase it, is this quantity here, let me draw a box around that like this. Is this quantity a random variable or a deterministic quantity? As I've written it here, it is a random variable because it has an x in it, right? It has a random variable x, and x is random. Therefore, x minus expected value of x squared is also random. And we don't want a random quantity, right? Expected value of x is not a random quantity. That's deterministic. It's a number. And so how could we take this quantity here and make it deterministic? An easy way to do this would be just to take another expectation. So what do I mean by that? I mean, we'll look at the following. To make my notation a little easier for the moment, because there's a lot of x's and e's flying all over the place, let's say mu is going to be my shorthand for the expected value of x. That's a deterministic quantity, right? That's a number. You give me any random variable, I can tell you what the expected value is. So mu is going to be my shorthand for expected value of x. And we're going to say the variance of x, we're going to write that as var of x like that. It's the expected value of x minus mu squared. So you have an expectation out here, which means this is a deterministic quantity. You're looking for the expected value of the random variable x minus its expectation, and then that whole thing squared. And that looks kind of ugly. Here's a way that you can simplify things, or here's a way that people find easier to work with. Just do some basic algebra. That expected value of x minus mu squared, if you expand that quadratic, and then you use linearity of expectation. So remember, the expected value of this thing, x squared minus 2x mu plus mu squared, is equal to the expected value of x squared minus 2 times the expected value of x times mu plus the expected value of mu squared, and that splits out like that. And now we'd say, well, mu is deterministic, right? We know what mu is. It's not random. And so therefore, there's no such thing as expected value of mu squared, this third term that I introduced there. It's just regular old mu squared because it's a deterministic quantity and it's not random. All I want to get at here is that I'm just trying to derive a simpler expression for variance, which you've probably seen before already, and it's this expression down here. Okay, this thing. It says the expected value of the quantity x squared minus the quantity expected value of x squared. We'll do some examples of this so you can see what this corresponds to. The whole purpose of this slide is just to tell you that variance is most often computed using this expression right here, and we'll do some examples of that. Sanity checks or discussion, first of all. The units of variance, the unit analysis, is as follows. If x is measured in miles, then the variance of x is measured in the expected value of x squared minus the expected value of x quantity squared. So the units of that would be miles squared, right? Because you're squaring things. And so you'd say, okay, variance has units of miles squared, x has units of miles, so they don't have the same kind of units. So how can I compare these two? What you typically do then is you define something called the standard deviation, which is typically written as the Greek letter sigma, and that's just the square root of the variance. So standard deviation, which is the square root of variance, is a nice quantity to work with because it's directly measurable. It's measured in the same units as the random variable itself, which is kind of convenient. So we often write sigma squared equals variance of x in the same way that we often write mu as for the expected value of x. You often just kind of as shorthand write things that way because a var x and expected value of x tends to get kind of large and cumbersome. There's almost linearity of variance, and not quite. Note that the variance of ax plus b is equal to a squared times the variance of x, and b does not appear at all in that expression. That's not surprising because what is, let me erase that so you can see it again. If I take this expression here, ax plus b, this thing here, what does that b mean? The b just represents an offset, right? It's you're adding a constant number to everything. Well, if I have a random variable and I add 912 to it, I'm not going to actually have any impact on the variance, right? I'm just going to affect where the variance or where the random variable tends to start and where it tends to end, which is to say I'd be affecting its expectation. But I'm not actually affecting how much it is spread out. So it's not. It makes sense that there is no b in this expression over here. And it turns out that if you multiply x by a scalar a, then the variance changes by a squared. That's just how variance works. And then if you were to take the standard deviation of that, you'd be square rooting this thing, which would bring that a squared back to an a as you want it to. I'll give you a reference table here. I have a more concise one in the next lecture, but I've written down here the expected value and variance of a bunch of discrete random variables and for a bunch of continuous random variables. So for a Bernoulli random variable, the expected value of x is just p. The variance of x is p times 1 minus p. For a binomial random variable, you can compute that the expected value of a binomial random variable is n times p, and the variance is n times p times 1 minus p. And the way you would derive those is you would derive them from the fact that a binomial distribution is just the sum of a bunch of Bernoulli random variables, and you'd use the linearity of expectation that comes with that. For a geometric distribution, the way you would derive this, you'd use the formula for the sum of a geometric series, or as I like to call it, you'd type it into Wolfram Alpha without having a clue of what's going on. The expected value of x by definition is just the sum over this geometric random variable of the PDF times the value itself. Again, this is just me plugging in the definition of expectation from a few slides ago, and you get 1 on p. And then the variance is this thing here, 1 minus p on p squared. You don't need to memorize any of these things. I'm giving them to you as a reference so you can refer to them whenever you like, and you don't have to go back and rederive these yourself or Google them or anything like that. For a Poisson random variable, the formula involves using a Taylor series for the function e to the x, e to the lambda rather. And you'd find that the expected value of a Poisson random variable is lambda, as is its variance. which is kind of strange. The variance for a Poisson random variable is actually equal to the mean, which is sort of weird because variance, as we talked about a minute ago, has different units from expectation. So, or different units from the random variable, which is kind of interesting. For continuous random variables, a uniform distribution, the expected value is a plus b on 2. The variance is b minus a squared on 12. For an exponential distribution, you would integrate by parts and find that the expected value is 1 on lambda and the variance is 1 on lambda squared. For a gamma distribution, deriving this is pretty hard. If you want to do it directly, if you want to use the fact that it's the sum of a bunch of exponentials, then you could derive this, although working it out for general k is kind of rough, but you don't need to worry about that because I'm giving it to you. The expected value of a gamma distribution is k on lambda, and the variance is k on lambda squared. Finally, for a normal distribution, you do a change of variables and you get the expected value of x is mu, and the variance of x is sigma squared. Again, you can refer to these anytime you like. Don't worry about deriving them. I'm just including them here so you can refer to them later. Jointly distributed random variables are what you get when you have two or more random variables that are related to each other, or they have some kind of relationship, right? Like the relationship between the weather and how long it takes for you to drive to work. Two quantities that are random and you think they have some kind of relationship between them. In some situations, in that kind of situation, you define something called a joint PMF or a joint PDF, depending on whether your random variable is discrete or continuous. So if you have a discrete random variable, whereas a PMF before was f of x, now we'd call that f of x and y. So f of xi and yi is just the probability that x is equal to xi and y is equal to yi. Y is equal to yj. And we call that Pij. So it's just a function of two variables that says the probability that each one is equal to a specified value. In the continuous case, we'd say the probability that x lies between a and b and y lies between c and d would be this double integral over a rectangle like that. That's a PDF for two random variables, or a joint PDF. And of course, both of these have to integrate or sum to 1. When you take them over the entire sample space. You could also define a joint CDF. So big F of x and y is just the probability that the first random variable is less than or equal to x and the second random variable is less than or equal to y. You don't really use this a whole lot, but you could define this. And so for a discrete random variable, that would be a sum over all the values where the entries are less than or equal to x and y respectively. And for a continuous random variable, you would just integrate. You would integrate from v goes to x and u goes to y over that sort of subquadrant there. Again, we don't usually encounter these much. I don't usually give problems that have that. Let's do an example. Let's do a discrete example. You roll some dice and you record two things. You record the sum of the values. So you roll 2 dice and you add the values together. So that's a number 2 to 12. And then y is going to be the smaller of those two values. As a simple example here, I've got 2 dice, and I can see that they're showing the number. If I add the two numbers together, I'd get an 8. And the smaller of those two numbers is the number 3. Oh, that's a 5. The smaller of those two numbers is the number 3. So rolling those 2 dice, a 5 and a 3, that would be x would be 8 and y would be 3. So the sample space and the PMF are what I've drawn here. So x, as I said, ranges from 2 to 12, and then y ranges from 1 to 6. And then I've written all of the possible outcomes here and their probabilities. So the one that I mentioned just now that I was holding up was x was 8 and y was equal to 3, and that has a probability of 1 in 18 of happening. This is not a great example because all the probabilities are either 1 in 18 or 1 in 36. Not the best example, but at least it requires some thought. Okay, so that's a joint probability mass function of two random variables, x and y. We say two random variables are independent if the two random variables have nothing to do with each other. Just like with two events. We showed that if we said two events are independent if their probabilities have no influence on one another. And the same is true for random variables. We say two random variables, x and y, are independent if the probability that the first random variable is less than or equal to x and the second random variable is less than or equal to y is equal to the product of the probability of the first variable being less than or equal to x times the second variable being less than or equal to y. Okay, equivalently, if you want to talk about things in terms of PDFs and PMFs, it is also accurate to say that x and y are independent if their PDF or PMF can be decomposed into a function of x times a function of y. Okay, so anytime you have a PDF or PMF and you can break it apart into a product of a thing in x and a thing in y, then you can immediately say, these two random variables are independent. If x and y are independent, then certainly the expected value of their product is equal to the product of their expectations. Okay, expected value of x times y is expected value of x times expected value of y. So that's what it means for two random variables to be independent. Let's do an example of this really quickly here to cover what we've talked about so far. Let's say we've got a joint distribution given by the following. So I've got f of x comma y is equal to this e to the power of minus x plus y for non-negative x and non-negative y, and then it's 0 everywhere else. So this is a random variable that's only defined in the positive quadrant. And we're going to do three things. We'll determine the probability that x is less than or equal to 1/2. We'll determine the probability that x plus y is less than or equal to 1. And then we'll ask the question and answer the question if x and y are independent. So how do we work this out? Well, to determine if x, the first part, the probability that x is less than or equal to 1/2, you would do this as follows. You would say, well, what do I need to do here? Let's take the PDF, which is e to the power of minus x plus y, and we'd integrate that thing from x going from, in this case, 0 to 1/2. This thing dx like that. Okay, we'd integrate that. And what would we be left with? We'd have a function of y now, right? Because there's an x and a y in my integrand, and I'm integrating out that x. And so I want x to be less than or equal to 1/2. Do I have any restrictions on y in this statement? No, I just said x is less than or equal to 1/2. Y could be anything we want it to be. And so therefore, I would integrate y from 0 to infinity, like that, and then I would evaluate that integral. And so we'll do that now. I've got the work shown in the slide, which I won't bother to spend your time on. If we look at bullet number 1 there, if that will load, there we go. This is exactly what I wrote there in my notes over there, and you find that that is equal to 1 minus e to the power of minus 1/2. Nothing terribly interesting there. As for the second problem, we want the probability that x plus y is less than or equal to 1. It's less than or equal to 1, and so we will draw some coordinate axes here. So we'll do that like this. I'll just draw, here's a y-axis and here's an x-axis. And I want x plus y less than or equal to 1, so that would be me taking this region here like that. This is 0, 1, and this is 1, 0. And I'd want the integral over this region here. If you remember back to multivariable calculus, how would you do this? Well, it's going to be a double integral, and we'll integrate with respect to x first. So we'll do e to the power minus quantity x plus y. That's the thing I'm integrating because I want a probability. And what happens to x here? Okay, what is the range of x? X starts at 0, and it goes up to this line here, and this is the line x plus y equals 1. Which means that x goes from 0 up to 1 minus y, like that. Okay, so we'd integrate x goes from 0 to 1 minus y, and then we'd integrate y going from 0 up to 1. And so we'd put a dy there, and we would evaluate this integral. If you go ahead and do that, as we'll do it now, you'd end up getting a 1 minus 2 on e if you just compute that integral, which again, you could use Wolfram Alpha for, you could use, Mathematica, Maple, whatever you like. The last question, are x and y independent? Often I get the answer, no, it doesn't look like they are. Actually, they are. And the way you'd work that out is you would just say, well, I'll make a little margin note right in here. I've got the answer written over there, but I'll do it here anyway. E to the power of minus quantity x plus y. If you remember your rules for exponentiation, that's just e to the power of minus x times e to the power of minus y. And that is a product of a function in x times a function in y. So indeed, those two are independent of each other. So x and y are independent for this example. Now let's talk about marginal distributions. A marginal distribution is what you get if you have a joint distribution on two variables, but you only care about one of them. So I give you a pair of two random variables like the dice example before, where you look at the sum and the lesser of the two values. And you say, well, I actually don't care about both of those variables. I just care about the sum, let's say. Or you have two random variables, and you say, well, I want to ignore one of them. I only care about the other one. And what you call that's called a marginal distribution. So if I give you a joint distribution f of x and y, that could be a PMF or a PDF, and I say, okay, well, I only care about x. Well, the way you would write that is you'd say f and then a little x in the subscript, and then a lowercase x there. That's a shorthand for me saying I'm interested in the distribution that only talks about x, and I don't care about y. So if I give you this joint distribution here, and I say I want you to restrict that just to x, so I only care about the randomness of x, or how x varies, you would write that as f and then a subscript there of a capital X and a lowercase x like that. Or if you're talking about y instead, you'd write f and then a subscripted capital Y and then a lowercase y. For the discrete case, all you do for this is you just sum over all of the values of the variable you don't care about. So if I'm interested only in x, if you give me a joint distribution on x and y, and I say I only care about x, then what you do is you just say, okay, the value of this distribution for x is just the sum over all possible values of y of the PDF. And for the continuous case, instead of a sum, you take an integral. So the distribution just on x is taken by integrating y from minus infinity to infinity. So you just integrate out, or you sum out, the variable that you don't care about. This is called a marginal distribution. Here's an example of recovering a marginal distribution when you're given a joint distribution. So let's say in this example, you've got a PDF that looks like this. You've got f of x comma y, and that is equal to 1 plus the sine of x plus y, and divided by, what is that normalization factor? 4 pi squared. 4 pi squared for x and y both between 0 and 2 pi. Okay, you could verify that the integral of this thing is equal to 1. That's what that 4 pi squared is for. And so let's compute these marginal distributions for x and y. So we'll do it for x first. The marginal distribution for x. So what do? I take this function here. I take that PDF, 1 plus sine of x plus y, divided by 4 pi squared. So this is a function of x, and what do? We integrate the y out. So we put a dy there, and we integrate y, and y for this problem ranges from 0 to 2 pi. So you integrate y equals 0 to 2 pi. And if I were to work that out, I won't bore you with the integration here, but if you do that, you would end up getting 1 on 2 pi for the marginal distribution on x. And if I wanted the same thing for y, f sub y of y, I would do the same integral, the same idea, but I would just integrate with respect to x instead. So I'd integrate this thing from 0 to 2 pi of 1 plus sine of x plus y on 4 pi squared dx. And you'd get, for both of these, you get 1 on 2 pi. Now, notice here in these examples, the ones I just did, that this, I said I wanted a distribution on x, and I actually just got a constant, like there's no x over here, right? And ditto, this is supposed to be a distribution on y, but there is no y over here. It's just the number. Okay, this is a special case, and this occurs because we have the situation where this marginal distribution, or both of these rather, they are uniform, right? Remember, a uniform distribution just has a constant value attached to it here, and so each of these have a marginal distribution which is uniform from 0 to for the first one, x goes from 0 to 2 pi, and the second one is y goes from 0 to 2 pi. So this is kind of a weird situation where if we look only at one variable, we see that that one variable is uniformly distributed, but the joint distribution of the two of them is very non-uniform. So this is kind of an unusual situation here. And so that's kind of unusual and kind of interesting. So that's what's going on there. Let's do covariance now. Covariance is something that measures how related two random variables are to each other. So if I have two random variables, x and y, and their expected values are mu and eta, let's suppose they're not independent, and we'd like to know how dependent are these random variables on each other, right? How related are they? The quantity that we use to measure this, we call it the covariance, and we write that as cov of x comma y, and it's the expected value of x minus mu, its mean, times y minus eta, its mean. And that ends up being more easily written just as this. It's the expected value of the quantity x times y, and then minus the product of mu and eta. This is 0 when x and y are independent, because expected value of the product is equal to the product of expected values. And I've worked out that I've worked out how you would prove that here, but you don't need to worry about that. You can accept it. You can accept that I'm telling the truth there. So properties of covariance. For any random variables x, y, and z, and any constant c, here's what is true. The covariance of x with itself is just the variance by definition. The covariance is symmetric, so the covariance of x comma y is equal to the covariance of y comma x. It is linear in the sense that, or bilinear, I think is the right term here, that if I multiply one of those random variables by c, that just jumps out over here. So covariance of cx comma y is equal to c times the covariance of x and y. And then finally, covariance is additive. The covariance of x with the random variable y plus z is equal to the covariance of x and y plus the covariance of x and z. Useful properties of covariance that will probably come up when you're working through your problem set. If x and y are independent, then here's something that's true. The variance of x plus y is equal to the covariance of x plus y with itself. You apply the linearity here, and you find that since the covariance term of x and y goes to 0 because x and y are independent, the variance of x plus y is equal to the variance of x plus the variance of y. So that's a useful fact, that if x and y are independent, then the variance of x plus y is equal to the sum of the variances. So you'll end up using this throughout the course a fair amount. In general, if x1 through xn are independent, then the variance of the sum is equal to the sum of the variances. You could use that fact to work out the variance of a binomial distribution or a gamma distribution for the case where k is an integer, if you wanted to do that. But you don't have to. That's one way you could derive that. Let's do some inequalities here to wrap this lecture up. The Markov inequality says for any random variable x that takes on only non-negative values and any positive scalar a, here's something that is always true. The probability that x is greater than or equal to a is less than or equal to the expected value of x on a. And the proof is actually not very hard. You could work this out here. The expected value of x is just the integral from 0 to infinity of x times the PDF. And of course, that's at least what you would get if you integrate this thing just from a to infinity. And then finally, because x has to be greater than or equal to a, you would find that that's at least as big as the integral of from a to infinity of a times the PDF, which is the quantity that you want. Again, don't worry about that derivation. I'm just jumping through it really quick if you want to know where the heck that reasoning comes from. The next one is the Chebyshev inequality, which I think we're probably not going to touch, but I'll include it here for completeness' sake. For any random variable x with a mean mu and a variance of sigma squared, and any non-negative k, we have this relationship here. The probability that x is more than k units away from its mean is less than or equal to sigma squared on k squared. This is a consequence of the Markov inequality from the previous slide, but I'll skip through it. Finally, we've got the strong law of large numbers. Actually, not quite finally. We've got to do the central limit theorem too. Strong law of large numbers says that if x1, x2, and so on and so forth is a sequence of independent random variables, and they all have the same distribution, and we'll say mu is the expected value of that distribution, then with probability 1, which is a term you don't ever need to worry about, it's just a formality to keep the probabilists happy, you have that the limit, as I take lots of samples, lots of independent samples, and take their mean, then that converges to mu. That converges to the expected value. Again, you're not going to need to touch this. You're not going to need to know it well. I just want to make sure you see it again in the language that we've been using the other aspects of the course for. So don't worry so much about that. The central limit theorem. Central limit theorem says that if you take a bunch of random variables and add them all together, then you get something that approaches a normal distribution. Okay, so to be more precise here, again, if I have a bunch of random variables, x1, x2, and so on up to infinity, and I add them all together, and I subtract n times their mean, and I divide that by sigma root n, then that random variable that I get approaches a normal distribution with mean 0 and variance 1. Really, all you want to get at here is this. If I take a lot of samples of a random variable, and then I take their sample mean, that thing follows a normal distribution with mean mu and variance sigma squared on n. Okay, but when we need this thing, we'll refer to it later. Don't worry if you're rusty on this. It's not a big deal. Stochastic processes. Stochastic process is just a collection of random variables indexed by time. We're going to use these when we look at Markov chains in a lecture or two from now. The way you'd usually write this is you'd write this as x of t, x parentheses t, and that represents the state of the system at time t. That index t, it could be continuous, it could be some continuously varying quantity, or it could be discrete, meaning it just takes integer values, 0, 1, 2, 3, and so on and so forth. The set of all possible values that this xt could take is called the state space. So what are some examples of this? X of t could represent the amount of customers in a store at time t. Right? You can say x of t is just how many customers happen to be in your store at a time t. Should t be discrete, like on the hour exactly, or should it be continuous, like you could measure the time at any point throughout the day? Either one of those would make sense. Okay? It could represent the amount of people in a family that reproduces randomly. You could look at a family tree and look at the lineage or the descendants of someone, right? Maybe their bloodline eventually runs out, and so then x of t is eventually 0, right? Or maybe it expands towards infinity forever. So x of t could be the number of members of a family that exist at any point in time. X of t could represent the position of a particle that is moving randomly along the real line, right? A Brownian motion, if you've seen that before, or the price of a stock, for example, something that is moving around. So it's a random variable that is indexed by time. It's where you'd say at any particular time, what is the value of this random variable? And that's of interest to you for one reason or another. A few other examples. You could say each day I wake up and I flip a coin. So each day I flip a coin, and on day t, x of t is 0 or 1, indicating heads or tails. So this is a really boring example because x of t is always just going to be 0 or 1. It's a heads or a tails. And each day's outcome is totally unrelated to the outcome from the day before. So it's not a very interesting example because x of t has nothing to do with xt minus 1 or anything like that, right? The time component doesn't really matter. A slightly more interesting example, but still kind of a boring one, would be that each day you flip a coin, and on that day you write down all of the heads that you've seen so far, right? So you flip a coin and you write down all the heads that you have seen since beginning this experiment. So then how could you write this? You'd say x of t is equal to x of t minus 1. So that's the thing that happened the day before. X of t minus 1 is how things were yesterday, plus yt minus 1, where yt minus 1 is a Bernoulli random variable, right? It's the coin flip. It's a 0 or a 1. The yt minus 1 is what I flip on that day and what I see. So what is true about this? What is true about this, number one, each x of t, on each day, the number that you write down, that distribution is binomial. Because on day t, you've had t attempts, and you flipped a coin, and you're recording how many times you have seen heads. So you're recording the number of successes. So that's a binomial distribution. Most importantly about this example, these values of x's of t's, they're not independent of each other, right? If I know that yesterday I had seen 5 flips, then today I'll either have seen 5 flips or 6 flips, right? It narrows things down. So these x of t's are not independent of each other, unlike that other example where you just write down x of t is 0 or 1, heads or tails. So that's a stochastic process. We're going to touch on that a lot later on, but for now, just be aware of that definition.